I want to talk about Newton's laws for rotation, how Newton's first and second laws relate in rotational concepts. In other words, how we apply those laws when we're talking about rotating things rather than things with their center of mass moving in a translational mode. So Newton's first law is if acceleration is zero, then sum of force is zero. In other words, constant velocity if it's in equilibrium. Let me write that in, equilibrium. I'll just abbreviate it there so I can keep seeing my pretty face. Newton's second law, really easy. Sum of forces equals m times a. And the direction of the sum of forces is the same as the direction of the acceleration. Well, there is an exact, and remember that this covers all of Newton's first law. If the acceleration is zero, the sum of forces has to be zero. So it's really just Newton's second law. So let me get rid of these. And so Newton's second law, if we think of it in a rotational sense, there's a very, very logical approach. And it's an analog, again, it's an analog or an analogy to the linear stuff. And this is it. Sum of forces equals ma. Okay, and that's translational. Rotationally, sum of, what's like force rotationally? Torque. Sum of torques equals something times the angular acceleration. And that something is related to, remember, this is kind of the inertia, inertial mass. Inertial mass is how hard it is to accelerate it, how hard it is to change its motion. It's distinct from gravitational mass, but they end up being equal in all the circumstances that we know of. Okay. But here, this is also an inertia. It's rotational inertia. What makes something harder to rotate? What gives it more rotational inertia? Well, clearly if it has more mass, but it's also related to how far away from the point of rotation the center of, the mass is. So it's really the distribution, mass and distribution of mass. It's kind of cool in its own way. Okay? And I'll do a completely separate thing on rotational inertia, but here's a concept of it. If I take this meter stick, hold it in the middle, how hard is it to rotate? Let me do it this way. Not that hard. It's pretty easy for me to go back and forth really fast, right? Whereas if I have it at the end, it's a lot harder for me to make it go back and forth quickly to change its rotational acceleration. And you can do that with a pencil or a pen. Right in the middle, no problems. And I do it vertically just so gravity's not such a big issue. At the end, you can sort of feel it's a little different. People change the rotational inertia. A person has rotational inertia, but it depends on what the point of rotation is. If this is my axis of rotation, the closer things are to the center, the easier it is to spin me. The farther things are, the harder it is to spin me. Okay? Similarly, if this is the axis of rotation, if I'm going to do a flip, right? If I do a flip while I'm fully straight, it's harder to spin me than if I'm curled up. Okay, and that's why you see divers curl up so they can rotate more easily. So that's how hard it is to change an object's angular velocity. Right? This is the angular acceleration. So I apply torque, it's like a force, to an object that we know the characteristics of how hard it is to change its state of motion rotationally, and we get an angular acceleration. Well, we call this the net force, we call this the net torque. Okay, how much more in one direction than another. And direction, remember, in AP1, we're going to be talking about clockwise and counterclockwise. So, really quick, let's look at just a standard example, like a seesaw. And seesaws, when I was young, every playground had a seesaw. And then people got really risk averse. And we got hurt on seesaws all the time. But a seesaw basically is an exercise in torque. You have a beam here, and you have a person over here. And what was really interesting about a seesaw is you didn't have to have the same weight. You could have a big person and a small person within reason, and they'd still be able to use a seesaw. So we've got a big kid here. If we have a little kid, well, we'd have to do some adjustments. Let's say we have a bigger kid over here. If I have a bigger kid over here, okay, and let's say they're both 2 meters away. It's a pretty big seesaw. Well, that's a good size. Okay, let's say they're both 2 meters away from the center, and this is going to be my point of rotation, P-O-R. Seesaw is going to rotate, let's just say they start from rest, if there's a net torque. Sum of torques equals I alpha. Let's not worry about the I right now, okay? But there's going to be an acceleration if there's a net torque, if there's an unbalanced torque, if it's out of equilibrium. We would like it to be in equilibrium, so these two, for the most part, tend to be balanced. So let's see what this person's torque is. This kid has a mass of 20 kilograms. This kid has a mass of 40 kilograms. Okay? If they just sit there, RF sine of 90 degrees, just because this thing is horizontal, and mg is pulling straight down. This is, by the way, 200 newtons. This force would be 400 newtons, mg. Okay. There is another force on the seesaw, but it's from this fulcrum, and it points right up through the point of reference. There's no torque there, point of rotation. I keep saying things wrong. So this torque would be, hey, we got a direction issue. Okay. I'm going to consider this counterclockwise, this clockwise. Eventually, I'll start putting a sign on that. But right now, I'm just going to write this torque is going to be 200 times 2, R is 2 meters, times sine of 90, which is 1. And that's 400. And I really do want to specify a direction, and that is going to be counterclockwise. This would be 400. The torque that this big kid puts on, times 2, times sine of 90, which is 1, because again, there's R, there's the perpendicular, the fact that they're perpendicular. And so you end up with 800. Look at me without units, Newton meters. This one, if he is the only force on there, it's going to make it rotate this way. That means it's a clockwise. So to figure out the direction of each individual torque, you look at it as if this is the only torque on there. This guy would make it go this way. And if you have to take a pen and go, if I push down here, oh, it makes it rotate counterclockwise. This one, if I push down here, makes it rotate clockwise. I'm going to start now developing good habits. I'm going to say, I'm going to call this direction positive. That's kind of the standard in physics, counterclockwise, positive. Okay? And again, this isn't a real vector. A real vector would be a straight line, but we're pretending for AP1, we're just going to define which way the net torque is. Okay, so 400 counterclockwise, that's going to be positive. 800 clockwise is negative. So the sum of torques equals I alpha. Substitute, we've got 400 plus negative 800 equals I alpha. Negative 400 equals I alpha. So this thing is going to be, that's just always how much, so it's going to be a positive number. That's going to be negative. That means it will accelerate in the clockwise direction. So that's how Newton's second law works with this. Okay, if I knew what I was, I could find alpha. Okay, very typically, it'll be more of a Newton's first law kind of problem. And the Newton's first law problem would be phrased as, where does this guy have to sit so it is balanced, so it's in rotational equilibrium? Okay, and for that to be the case, let me get rid of most of this stuff. So we want to find out how far away from that point of rotation this 40 kilogram kid has to sit. Okay. So let's draw that seesaw again. Oh, and there's another force. I forgot. There's another force. There's mg on the seesaw. But if the center of mass of the beam is right over that fulcrum, we'll be okay. Okay, because it will not have a torque. There's no R. Okay, so here's this kid now. He's moved in somewhere, right? So his force is still 400 newtons. And so the sum of torques, we want it to be 0. We want there to be no angular acceleration, and that means it's in equilibrium. So let me rewrite this whole thing. So sum of torques equals 0. Where does he have to sit? Well, this one still has the same torque, 400, plus this will be in the negative direction, F 400 times R, we're trying to find out what that R is, times the sine of 90, assuming he's pointing in the same direction, which is just 1. So we have 400 minus 400R equals 0. R ends up being 1 meter. So he has to scoot halfway in. He has to scoot in to the 1 meter mark. Now they're balanced, okay? And so there's no net torque caused by their weights, okay? It's a little weird thing. So if this guy pushes off, they're going to go at a constant velocity in this direction. It's going to be a little off because some things change. As he moves, their torques will change somewhat because they end up being the angle between R and F changes. That's way more complicated than I want to work with. But bottom line is his torque and his torque at the beginning are approximately the same. So you'll see kids on playgrounds, not so much anymore because they took them all off, but if you ever see a seesaw, they can go up and they can go down. They don't have to weigh the same amount. They simply have to have equivalent torques to be in rotational equilibrium. Okay? And remember, the thing that was most tricky about Newton's first law was constant velocity. So just because torques are equal doesn't mean that they're at rest. It just means the acceleration is 0. So anything that's moving around at a constant angular speed is in equilibrium rotationally, is in rotational equilibrium. The sum of torques has to be 0. It's not speeding up or slowing down. It doesn't mean there are no torques on it, it just means they're balanced. So for example, a car driving at 30 miles an hour, you've got a tire, okay, and the tire is pushing back on the road is pushing forward, force of friction on the tire as the car is moving in this direction, okay, and there's other friction and air resistance slowing it down, applying torque in another direction. It's a little more complex, but it ends up being in equilibrium if they're driving at a constant velocity. So how do you solve Newton's second law problems for one body? Sum of torques equals I alpha. You define your frame of reference. Remember what we did. Newton free body diagram. Now you want to do what's called a force diagram where you show where the forces are applied. Okay, so force diagram, frame of reference, define a positive direction, and then a Newton's second law. I'm going to say the rotational version. Instead of sum of torque equals, instead of sum of F equals IA, it's sum of torques equals I alpha. And I just said that wrong. Sum of F equals MA, torque equals I alpha. Okay, so if you keep those all straight, and we'll do a bunch of problems, you're going to be really fine with torque. It is no different than all the old Newton's second law stuff we did.